The signal takes more than 19 hours to arrive. It travels at the speed of light, 186,000 miles per second. And it still takes 19 hours. That is how far away it is. That is how completely, staggeringly, almost incomprehensibly far a 47-year-old spacecraft built from 1970s technology has managed to travel while still sending data home. Still functioning? Still measuring. Still telling us things about the universe that nothing and no one else has ever been in a position to report. Voyager 2 is currently more than 13 billion miles from Earth. It crossed beyond the boundary of our solar system in November 2018, becoming only the second human-made object in history to reach interstellar space. The vast, cold, ancient ocean of plasma and magnetic fields and cosmic radiation that fills the space between stars. And what it found there, on the other side of the boundary that separates everything our sun has ever touched from everything it has not. It was so different from what scientists expected that 5 separate papers were published simultaneously in the journal Nature Astronomy to process the implications. Not 1 paper, 5. Because what Voyager 2 measured as it crossed that boundary was so multidimensional, so layered with surprise, that no single paper could contain it. This is not a story about a mysterious signal or an alien warning or a conspiracy that NASA is hiding from you. This is a story about something far more extraordinary than any of that. This is the story of what actually happens at the edge of our solar system. At the precise boundary where the sun's influence ends and the galaxy begins, and what a spacecraft launched in 1977 with less computing power than a modern digital thermostat has been teaching humanity about the true nature of the space we inhabit. The real story is stranger, more unsettling, and more profound than any fabricated version of it could ever be. To understand what Voyager 2 found, you need to understand what it crossed. The heliosphere is the word scientists use for the enormous bubble of influence that our sun creates around itself. The sun constantly exhales. It streams a continuous flow of charged particles outward in all directions at speeds of hundreds of kilometers per second. This is the solar wind. It rushes past Mercury, or Venus, Earth, Mars, past the asteroid belt, past Jupiter and Saturn and Uranus and Neptune, past Pluto and all the other small worlds of the outer solar system. And then gradually, it slows, it decelerates, it stacks up against the pressure of the interstellar medium, the gas and dust and plasma that fills the space between stars. That is not the sun's creation, that belongs to the galaxy itself. Where the solar wind finally stalls and the interstellar medium takes over is called the heliopause. It is the technical, physical, measurable boundary of our solar system. The shoreline, where our sun's ocean ends and the galactic ocean begins. Before Voyager 1 crossed the heliopause on August 25, 2012, scientists had calculated roughly where it should be, but no one had ever measured it directly. No human instrument had ever been there. Everything we thought we knew about the heliopause was modeled, estimated, extrapolated from data collected much closer to home. Voyager 1 became the first probe to cross it, and what it found surprised researchers in several ways. But Voyager 1 had a critical limitation. Its plasma science instrument, the device designed specifically to measure the charged gas that fills both the heliosphere and interstellar space, had stopped working correctly in 1980. Scientists could infer from other instruments that Voyager 1 had crossed the boundary, but they could not directly measure the plasma transition. They could not take the temperature of what lay on the other side. They could not record the precise density jump that the physics predicted should happen at the heliopause. Voyager 1 saw the boundary. It could not fully describe it. Voyager 2 changed that. When Voyager 2 crossed the heliopause on November 5, 2018, at a distance of 119.7 astronomical units from the Sun, about 11.1 billion miles well beyond the orbit of Pluto, its plasma science instrument was still working. It was the only instrument of its kind ever to directly sample the plasma environment at the heliopause and on both sides of it. And what it recorded in the days and hours around that crossing produced measurements that researchers are still working to fully understand. The crossing itself was shockingly abrupt. Not gradual. Not a slow transition through a fuzzy, blended zone where solar material and interstellar material gradually mixed. The heliopause, as Voyager 2's instruments measured it in real time, was extraordinarily thin. There was a boundary region about 1.5 astronomical units wide, roughly 140 million miles, where the solar wind plasma slowed, compressed, and heated as it stacked up against the pressure of the interstellar medium outside. Inside this region, the plasma density was twice what it had been in the typical heliosheath, and then, just 0.06 astronomical units inside the heliopause, an almost negligibly thin sliver of space. Came a final transition layer where the radial speed of the plasma dropped sharply, the density spiked, and the magnetic field strength increased abruptly. And then Voyager 2 was through. The entire transition, from heliospheric plasma to interstellar plasma, was completed in less than 1 day. The boundary between our solar system and interstellar space is, by astronomical standards, a razor's edge. When the cosmic ray instruments recorded what was happening simultaneously, they confirmed the crossing in a different way. Inside the heliosphere, the sun's magnetic field deflects and blocks a significant fraction of galactic cosmic rays, high-energy particles accelerated by exploding stars and other violent events throughout the Milky Way. So Voyager 1 had already established that the heliosphere blocks more than 70% of this cosmic radiation, shielding all the planets, including Earth, from bombardment that would otherwise be far more intense. When Voyager 2 crossed the heliopause, the instruments measured a sudden sharp drop in the solar particles that permeate the heliosphere. They essentially vanished, while the rate of galactic cosmic rays jumping inward from outside increased dramatically and held high. The transition was simultaneous, sharp, and unmistakable. The sun's protective shield has an edge, and Voyager 2 crossed it in less than 24 hours. But the most surprising measurements came from what lay immediately on the other side. The very local interstellar medium, the region of interstellar space just beyond the heliopause, turned out to be significantly hotter than any model or prior observation had predicted. When Voyager 2's plasma instrument measured the temperature of the plasma in this region, it recorded temperatures between 30,000 and 50,000 Kelvin. Models and prior observations had predicted the local interstellar medium temperature to be somewhere between 15,000 and 30,000 Kelvin. The actual temperature was nearly double the upper end of the predicted range. Some researchers believe the excess heat comes from the compression of interstellar plasma as it presses against the heliosphere. The material piling up like snow in front of a snowplow, compressing and heating as it accumulates. Others argue magnetic reconnection, a process where opposing magnetic field lines break and reconnect, releasing large amounts of energy, is contributing to the elevated temperatures. Both processes may be occurring simultaneously. The interstellar medium is not the quiet cold, or empty void of popular imagination. It is dynamic, energetic, variable, and substantially stranger than the models had captured. The magnetic field measurements added another layer of astonishment. One of the puzzling findings from Voyager 1's crossing in 2012 had been that the magnetic field direction did not change when the spacecraft crossed the heliopause. This was unexpected. Inside the heliosphere, the magnetic field is dominated by the sun's own field. Outside the heliopause, in interstellar space, the field is carried by the interstellar plasma from the galaxy. These two fields were expected to point in different directions. The sun's field and the galaxy's field are not aligned. But Voyager 1 had found that they were aligned, or very nearly so. Researchers were uncertain whether to trust this finding. Voyager 1's plasma instrument wasn't working, and some scientists worried the crossing had not been cleanly resolved. Perhaps the apparent alignment was coincidence, or a measurement artifact, or specific to the unusual geometry of Voyager 1's trajectory. Voyager 2 resolved the question definitively. Its magnetometer confirmed the same finding independently, from a completely different location in the heliosphere. Voyager 1 had exited near the heliosphere's leading edge, where it presses into the interstellar medium head-on, while Voyager 2 exited from its left flank, exiting in a direction roughly perpendicular to Voyager 1's trajectory. Despite this difference in location, the magnetic field alignment was the same. The external interstellar magnetic field is parallel to the solar magnetic field at both crossing points. This is not coincidence, this is physics. But physics that the theoretical models did not fully predict. What it means for the large-scale structure of the heliosphere and its interaction with the surrounding interstellar medium is still being worked out. What is certain is that Voyager 2's independent confirmation of Voyager 1's finding transformed it from a possible anomaly into an established fact. What also emerged from the 5 Nature Astronomy papers, when you read them together as a coordinated portrait of the heliopause rather than separate instrument reports, was the discovery that the boundary leaks in both directions. Voyager 2 found evidence that some interstellar plasma was penetrating inward through the heliopause before the spacecraft fully crossed it. And it found evidence on the other side that some heliospheric particles had leaked outward into the region just beyond the boundary. The heliopause is not a perfect seal. It is a dynamic, permeable frontier, a zone where the two great plasma systems, the heliospheric and the interstellar, interpenetrate at their edges through mechanisms including magnetic reconnection and diffusion. The protective bubble our sun has built around its planets is real, and it blocks the majority of galactic cosmic radiation. But it is not a wall. It breathes. It allows a fraction of what is outside to come in, and a fraction of what is inside to flow out. Understanding exactly how and why matters enormously for understanding how much cosmic radiation actually reaches the inner solar system over geological timescales. and what that might mean for the history of life on Earth. There was also a profound structural difference between Voyager 1's crossing and Voyager 2's crossing that the 2019 papers documented. When Voyager 1 approached the heliopause in 2012, its instruments detected what appeared to be flux tubes, channels where interstellar magnetic field lines had penetrated into the heliosheath, creating pathways for interstellar particles to stream inward before the crossing itself. These precursors appeared weeks before the actual crossing and gave scientists their first hint that Voyager 1 was approaching the boundary. When Voyager 2 approached the heliopause 6 years later, its instruments looked for the same precursors. They were not there. No flux tubes, no advanced signature of approaching interstellar material. Voyager 2 simply arrived at the boundary and crossed it, sharply, cleanly, and without the precursors that Voyager 1 had experienced. This difference matters because it reveals that the heliopause is not uniform. It behaves differently in different places. The two probes exited the heliosphere at different locations and at different points in the Sun's approximately 11-year activity cycle. The period over which the Sun's output waxes and wanes between solar minimum and solar maximum. Scientists had long theorized that the heliopause could expand and contract as solar activity changes, like a lung inflating and deflating. The differing experiences of the two probes in two different directions at two different phases of the solar cycle suggest that the heliosphere's boundary is not a static geometric shape, but a dynamic, variable structure that responds to both internal solar activity and external interstellar conditions. We crossed the boundary at 2 points. Those 2 points look substantially different from each other, and we have no data at all on what the heliosphere looks like in the vast majority of directions it extends. Its full shape remains genuinely unknown. This is not a small admission. The heliosphere is the structure that makes complex life on Earth possible by shielding the planet from the majority of galactic cosmic radiation over billions of years. Its shape, its stability across geological timescales, its response to changes in the galactic environment through which the solar system moves, these are not academic questions. They bear directly on the long-term habitability of Earth and any other planet inside any stellar system. And we are only beginning, with Voyager's measurements, to understand what this boundary actually does and how it actually behaves. Meanwhile, the spacecraft itself is engaged in a slow, irreversible process of dying, and the engineers managing it are working with extraordinary skill and care to delay that process as long as possible. The Voyager 2 launched on August 20th, 1977. It is powered entirely by a radioisotope thermoelectric generator, a device that converts the heat from decaying plutonium-238 into electricity. At launch, it generated 470 watts. Plutonium-238 has a half-life of 87.7 years, meaning the power supply decreases by about 4 watts every year as the radioactive material slowly decays. By 2026, the power budget has become so constrained that the mission's managers face an ongoing series of painful choices about which instruments to sacrifice in order to preserve the others. In October 2024, NASA turned off Voyager 2's plasma science instrument, the very instrument that had delivered those landmark heliopause measurements in 2018, to conserve power for the remaining 4. In March 2025, the low-energy charged particle instrument, which measured ions, electrons, and cosmic rays originating from both inside and outside the solar system, was powered down. The cosmic ray subsystem is scheduled to go dark in 2026. With each instrument lost, the picture Voyager 2 can paint of the interstellar medium becomes less detailed, less complete. By sometime in the 2030s, if the spacecraft survives that long, it will likely be operating a single instrument, watching, measuring, transmitting home with whatever power remains in a plutonium core that has been burning for more than 50 years. Voyager project manager Suzanne Dodd at JPL put it in terms that are both pragmatic and haunting. She said, "Every day could be our last." Not a dramatic warning to the world, a quiet, honest acknowledgement that they are operating at the absolute margin of what the engineering allows. Oh, and that every additional transmission is a gift that could stop without warning. The thrusters that maintain Voyager 2's orientation, keeping its antenna pointed toward Earth so the signal can reach home, are clogging in their hydrazine injectors. There are no backup thrusters left. Everything aboard this spacecraft is, as JPL's own project manager acknowledged, running on single string. One failure anywhere in the chain, thruster, computer, power system transmitter, and the signal stops. And because the spacecraft is more than 13 billion miles away, there is no repair, there is no recovery, there is no crew to dispatch. What breaks stays broken. The golden record is still aboard. It will be there long after the transmitter goes silent, long after the power source fades below the threshold for any active system to function. The record? A 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. was designed not as a message to anyone alive now, but as a message to any intelligence that might encounter it in the incomprehensibly distant future. Carl Sagan, who chaired the committee that assembled the record's contents, understood that Voyager would outlast the civilization that built it by many orders of magnitude. The spacecraft will drift through interstellar space for billions of years after its last transmission. In about 40,000 years, it will make a distant pass of a star called Ross 248. In about 296,000 years, it will pass within 4.3 light-years of Sirius, the brightest star in Earth's night sky as seen from Earth. At every point on that journey, the golden record travels with it, intact, essentially indestructible, I carrying the sound of rain and the Brandenburg concertos and greetings in 55 languages, and the brainwaves of a young woman in love. What Voyager 2 is sending back right now is data, measurements, numbers that describe the interstellar medium in terms of magnetic field strength, plasma wave activity, and cosmic ray flux. The three instruments still operating as of 2026, listening to the space between the stars with instruments designed when the personal computer did not exist. Those numbers are being analyzed by scientists at JPL and universities around the world who are building a picture of the environment our solar system is actually moving through. Not the idealized theoretical model, but the real, variable, complex, surprising reality that only in situ measurement can reveal. Ed Stone, who served as Voyager project scientist for 50 years from the mission's inception until his death in June 2024, said something that stays with anyone who heard it. He said the Voyager probes are showing us how our sun interacts with the stuff that fills most of the space between stars and the Milky Way. For most of human history, we had no way to know what that interaction looked like. We could theorize, we could model, we could estimate from the distant safety of Earth's orbit. What we could not do was go there and measure. Now we have gone there. 2 spacecraft launched in the same month in 1977, before most of the scientists now analyzing their data were born. I crossed the boundary of the solar system 6 years apart and from 2 different directions, and sent back measurements that confirmed some things we expected, overturned others, and revealed a boundary that is thinner, more complex, hotter, more permeable, and more variable than any model had fully captured. The signal takes more than 19 hours to arrive. It comes from a spacecraft the size of a small car, running on power equivalent to a dim light bulb, transmitting at a rate so slow it would take hours to send a single photograph. And when it arrives, it tells us things about the universe that nothing else can. That the boundary between our solar system and the galaxy is less than a day's crossing. That the interstellar medium beyond it is hotter than we thought and stranger than we imagined. That the shield our sun builds around its planets blocks 70% of the cosmic radiation the galaxy generates. That the shield leaks, that it varies, that it surprised us. Voyager 2 has been in space for 47 years. It has never stopped working harder than anyone expected, and it is not finished yet.